All right, everyone, welcome. In today's video, we're going to begin talking about power series. So previously, before, we've learned about what series are in general. So a series is the sum of an infinitely long list of numbers, or a sequence. And today we're going to learn about a different variety of series called a power series. So let's see the difference between that and the type of series that we're maybe used to. So previously, when we had a series, it started at one number n, went to infinity, and there was some sequence that we ended up adding up. So for example, this is the harmonic series, as you may well know, and its sum is 1 plus a half plus a third plus a fourth, and that goes on forever. Previously, we learned about a lot of different ways to tell whether or not this series converged or diverged. What we're going to do now is, instead of having a formula involving n for our series, we're now going to introduce having a variable as part of our series. So let's take this series, for example, the sum from 0 to infinity of x to the n. So if we begin plugging in these n's right here, it still does involve n in some way. X to the 0 for any x will be 1, and then I have n equals 1, that'll be an x. N equals 2 will give us an x squared, x cubed, and so on. So earlier in the semester, I've been hitting at these infinitely long polynomials which can represent functions. And this is exactly what this is. This is a power series, and this is what we're going to be studying next. Now, this x is a variable, right? So depending on what I decide to substitute in for that variable, this series could converge or it could diverge. So let's try some different x's for this series. How about x equals 1/2? Let's plug that in. So this is the sum from 0 to infinity. We put it exactly where the x is, 1/2 to the n. That'll be 1 plus a half, plus a quarter, plus an eighth, and so on. And you may recognize what type of series this is. This is called a geometric series. And since the absolute value of this number, 1/2, is less than 1, we know that this series is going to sum to 1 minus 1 over a half, aka 2. When we plug in x equals 1/2, this series converges, and it converges to 2. Now, speaking of 2, why don't we try to plug that into our series and see what happens? So this is the sum from 0 to infinity of 2 to the n. So we're adding up all these positive powers of 2. 1 plus 2 plus 4 plus 8 plus 16. And I think it's pretty clear, if we use the test for divergence on this, that this is going to diverge, since powers of 2 do not go to 0. So if we plug in x equals 2 for this series, then unfortunately it's going to diverge. So the question becomes, when we have a power series, what x are we allowed to plug in, and what x are we not allowed to plug in? And how do we find out what x's will work? Because, I mean, there are infinitely many real numbers. I can't just manually plug in all of them for any given series. So what are we supposed to do? Well, this is where the ratio test comes in. So earlier in the semester, I mentioned that the ratio test would be one of our most useful tests, and this is going to be where it shines. So let's take our series that we were just looking at, n equals 0 to infinity, x to the n. And let's suppose we wanted to know what x are okay to plug into this series and what x are not okay. What we could do is we could use the ratio test on this series. I mean, it's still a series, so we could still use the ratio test. Remember, the ratio test has us look at the limit as n goes to infinity of the absolute value of this, just with n plus 1 plugged in, divided by the original. And usually when we do the ratio test, we have some sort of fraction going on, but this is a very simple series. Now, if we simplify this x to the n cancels with all but one of these x's up here. So we end up with the limit as n goes to infinity of absolute value of x. But the thing with this limit here is that this is the limit as n goes to infinity. So there aren't any n's left right there, so the limit can just go away. This is effectively a constant with respect to that limit. So the result of our ratio test and our limit is just absolute value of x. Now, before, most of the time, the absolute values didn't really play a big role, since most of the things we were looking at were positive. But in this case, I can potentially have negative values for x. So it's important that we include those now. All right, well, anyways, absolute value of x. Remember, the result of the ratio test has to be less than 1 for the series to converge, and in fact, converge absolutely. So we know that for any number that has absolute value less than 1, it's safe to plug it in to this series right here. And by the way, since this is x to a power, even as a power series, this is still referred to as the geometric series. All right, now you may remember about the ratio test that it also has two other outcomes. If absolute value of x is greater than 1, or a result is greater than 1, it's going to diverge. So that's why 2 to the n didn't work for x earlier. But the sort of middle case or edge case, absolute value of x equals 1, remember the ratio test is inconclusive for that. So we need to check those points manually. So the two values of x that make its absolute value be 1 would be x equals plus or minus 1. And what we need to do is we need to plug those in for x and then use a different series test besides the ratio test. So let's plug in x equals 1, see what happens. That means our series is going to be the sum from 0 to infinity of 1 to the n, or just 1. So this series, we're adding up a bunch of 1s over and over and over, and pretty clearly it's going to diverge by test for divergence, because 1 does not go to 0 as n goes to infinity. And then in a similar way, we have negative 1. This is the sum from 0 to infinity of negative 1 to the n. And for the same reason that 1 didn't work, negative 1 to the n also won't work. We're going to keep oscillating between 1 and 0 if we keep adding those up. So it seems like neither of these endpoints ended up working. But don't let that fool you in the future. Sometimes our endpoints actually will make the series converge. So we know now that if we pick any x in negative 1 to 1, not including endpoints, then it's going to converge the series. And what we do is we call this set of points the interval of convergence. And you'll often see this abbreviated as IOC, because 3 words is too much. And then there's also something called the radius of convergence. So notice how absolute value of x is less than 1. This 1 tells you roughly how big this interval of convergence is going to be. So half the width of the IOC is called the radius of convergence. So this has a width of 2, the difference between negative 1 and 1, so its radius of convergence would be half that, or 1. Another way you could tell what the radius of convergence is going to be is if you get absolute value of x plus or minus a number less than a number, whatever number is on the right side of that inequality will be your radius of convergence. So anyways, we're able to figure out what numbers are safe to plug into this series. Why don't we take in another series? So this one may have already been familiar to us because it's the geometric series, just with an x instead of whatever other letter we used. Well, let's take a look at something more complicated that may not be as familiar. So let's say we have the sum from 1 to infinity of 2 to the n, x to the n, divided by n. So this is also a power series, because if I begin plugging in these numbers here, I'll end up getting powers of x. So how about we try to find what numbers are okay to plug into this series? So let's see here. As before, we'll do the ratio test. This is the limit as n goes to infinity of the absolute value. Now this time we have a fractional sequence that we're adding up. So what we're going to do is we're going to stick n plus 1s in the original and then multiply by the reciprocal with n's. So this will be our ratio test here. And once again, we can't forget to use the absolute values for this. Now, let's see how this is going to cancel. So we have 2 to the n plus 1 over 2 to the n. We're just going to end up with a 2 for that one. Same thing with the x's. We'll just have a single x on top. So let's write what we have now. What I'm going to do is I'm going to take this absolute value of 2x out here. And then we also have n over n plus 1 left over. We haven't done anything with that yet. Now, what I'm going to do is I'm going to get rid of the absolute values for those, because any n we're working with, we're at worst working with 1, is going to make this positive. So it's okay to not have absolute values. Now, kind of like before, this absolute value of 2x has nothing to do with a variable for our limit n. So what we could do is we can move this outside of the limit. We have absolute value of 2x times the limit as n goes to infinity, n over n plus 1. But now we have this limit right here, and it's a polynomial over polynomial or a rational function. The degrees on the top and bottom are the same, and they have the same leading coefficient, meaning this limit is 1. So all in all, we end up with absolute value of 2x for our ratio test. And remember, whatever we get from a ratio test needs to be less than 1. Now, it's helpful at this point to get the absolute value of x on its own. So what I can do is I can move the 2 out of the absolute value because that's already positive, and then I could divide both sides. So it turns out that all of the x values that have absolute value in between, or absolute value less than 1/2, will end up making this series converge. But as before, what happens if this number is exactly equal to 1, or this number is exactly 1/2? What about that? Well, let's take a look at that case. I'm going to leave this series up here for a moment. So for now, the result of our ratio test is this. But we need to check out the 2 points that have absolute value equal to 1/2, which would be x is plus or minus 1/2. All right, so let's try the positive one first. Let's plug 1/2 into here. And remember, we can't use the ratio test now, because we plugged in that x, we would get 1 for the ratio test. So this looks like it's going to be the sum from n equals 1 to infinity of 2 to the n times 1/2 to the n divided by n. But if we take the product of 2 to the n and 1/2 to the n, those will just cancel out to be 1 to the n. So these guys cancel out, and we effectively just have 1 over n. But as we know, this is the harmonic series, so it diverges by the p-test. So we wouldn't include positive 1/2 in this interval of convergence. On the other hand, though, let's say we had x is negative 1/2. Then we're going to have the sum from 1 to infinity of 2 to the n, negative 1/2 to the n, divided by n. Now this time, when we multiply those exponentials together, we'll instead get negative 1 to the n. And that'll be divided by n. Now this time, since this is an alternating series, it's monotonic, and its limit goes to 0, or at least the part attached to the alternator is monotonic. That means that this is going to converge by the alternating series test. And with this endpoint stuff, we don't need to worry about whether or not it converges absolutely or not. We just need to see if it converges at all. So it actually does end up working for negative 1/2. That means our interval of convergence would be negative 1/2, including that, to 1/2, but we would exclude the positive half. So sometimes we include one point and then we don't include the other. And what's the radius of convergence? Well, remember, we can always take a look at this number to get that. Our radius of convergence is going to be 1/2 as well. Okay, so that's that example. We found another interval and radius of convergence. Let's take a look at one more example here. So the next example is actually going to be something that we're going to be seeing a lot. So it's good to get used to this. So let's say we have the series of from n equals 0 to infinity of x to the n divided by n factorial. Okay, so we have a factorial in here now. Now, as usual, what we're going to do is we need to learn, okay, what numbers can we plug in safely to this series? So I'm going to use my ratio test. I have the limit as n goes to infinity. I replace these with n plus 1s, x to the n plus 1 over n plus 1 factorial, and then I have the reciprocal of the original. Remember, once again, we can't forget about our absolute values. They definitely make a difference for this. Now let's see, as always, the x's will cancel to just leave a single x on top. And then remember the way we cancel out these factorials. If I have an n plus 1 factorial down here and n factorial up here, n plus 1 factorial has all of the terms that n factorial does, and it has n plus 1. So what will happen is we'll just be left with a single n plus 1 on the bottom. This looks like the limit as n goes to infinity. Only the x could potentially be negative. This n plus 1 can't possibly be negative, so we're just going to leave it like that. Now, this time we actually have x's mixed in with our limit here as n goes to infinity. This time it's going to be 0, because absolute value of x is going to be a constant, and then we have 1 over n plus 1. That will head to 0. And remember, whatever our result is going to be less than 1. So it seems like this example is a little bit funny because it seems like no matter what x we end up picking, this could be like a billion, for example, eventually that n+1 will make that be insignificant. So it doesn't seem like it matters at all what x we pick for this series. It will still converge no matter what. And when that happens, we say that our interval of convergence is all real numbers. No matter what number I pick, I can safely plug it in to this series right here. Another way of writing this is you could write an interval notation with negative infinity to infinity, or if you happen to be in the know with some fancy math terminology, you could also do this double striked R right there. That also represents all real numbers. And what about the radius of convergence? Well, when we have an infinite interval of convergence, our radius of convergence is just said to be infinity. So that'll be our radius of convergence. Now this series will actually show up quite a bit in the future, and it's actually pretty nice that it has an infinite interval of convergence. Well, anyway, as always, if you have any questions on this video, let me know, and I'll do my best to help you out.